Coca-Cola Company is interested in obtaining more uniform fill heights in the bottles. The filling machine, in theory, fills each bottle to the correct target height, but in the practice, there is a variation around this target. So the company would like to understand better the sources of this variability. The process engineer can control three variables during the filling process: A, the percentage of carbonation; B, the operating pressure in the filler; and C, the bottles produced per minute. Coca-Cola decided to run two replicates of a factorial design in these three factors. Particular problem, we already mentioned that the engineer can control three factors. In this Excel file can be found in this table with represented with the letter A from the percentage of carbonation, B from the pressure, and C for the line speed. These three factors at two levels, a low one and a high one. It is important for me to mention that all of this information I obtained it from problem 6.20 from the textbook of Douglas and Montgomery, Design and Analysis of Experiments, where the data given me were the fill height deviation with two replicates. So it is important that we understand the background from this experiment. These numbers that we found that has the negative sign is because the fill height is below the normal fill, and the ones that has a positive sign, like these two, is because they're above the normal height. These zeros actually are the values that we wanted, because these represent that we don't have a deviation in our fill height. So with this information, this table can be filled. This A is the same A as this one, so it represents the percentage of carbonation. This B is the pressure, and this C is the line speed. These three factors are at two levels, a low one and a high one. This N corresponds to the number of replicates that we have in our experiment, that in this case I already mentioned that are two. This capital N corresponds to the total number of data that the experiment gives us, that in this case are 16 numbers. So this type of problem is two factor to the K, where this K corresponds to the factors that we have. So in this case we have three. This treatment combination can be obtained by our coded factors from our table of signs. Because we have replicates, we can do the Yates algorithm. So in this first number, what I did was the sum of these two numbers. From this, I do exactly the same. In the next one, exactly the same. This is exactly the same, but we find out that in this case, we now are doing the rest from this number to the top number that we have here. We do it 3 times because we have 3 factors, and this number that I color in green is the ground total. All of these numbers are called the contrast numbers. With these contrast numbers, we can now calculate our effects. Our effects are calculated with this contrast divided by the number of replicates times 2 to the k minus 1. Due to the fact that the data that they gave us has replicates, this means that the degrees of freedom of the error are enough to make our analysis of variation with all of the factors and also with the interactions of them. The sum of squares can be calculated with the square of the contrast that I already showed, which were the contrast divided by n times 2 to the k. The mean standard is just the division of the sum of squares divided by the degrees of freedom. We said that our null hypothesis is rejected when the f-test of the table is smaller than the f-test statistic. This f-test statistic can be calculated with the mean standard of each of the factors and also the interactions of them divided by the mean standard of the error. The f-table can be calculated graphically with our f-table at a degree of freedom of 0.05. With this information, we obtain that the factor A, B, and C are the ones that are significant of variation. We can obtain the model for predicting the field high deviation. This model is constructed here with J that is equal to our grand total that I can remind you we colored in green at the beginning of this problem, divided by the capital L that it corresponds to the total number of data that they gave us in the first part of the problem, plus a half of every effect of the significant variation source. Also, the effects we already calculate at the beginning of the problem. We have to copy this model 8 times, and here we are going to replace with the coded that we already see in our first part of the video, also that with our coded table we can replace these numbers, and by doing this equation we are going to find these answers that are going to help us to construct our counterplot that it's going to be shown to you at the end of the video. We can continue working with the calculation of our residuals. Residuals are calculated by the subtraction of the observed minus the expected, where the observed corresponds to the grand total that we already calculate, that this corresponds to the sum of the two replicates that the problem gave us. The expected value corresponds to the results obtained by our model of the high deviation. By calculating them, we can now put them in this little table that I have over here, where I put a place to each one of these residuals. I rearrange the residuals from low to high, and I calculate the probability. This probability is calculated by the place minus a half divided by the number of factors that we are working on. We can plot our residuals. Residuals plot has as the horizontal axis the residuals, and in the vertical axis the probability. We made this square around the 0 that corresponds to the 3 and the 1 quartile, and we made this line that corresponds to the linear regression. We have these two numbers that are very far away from the rest of the residuals that we plot, but also these two numbers outside of our square. So we have to test for outlier of these four numbers to see if it is significant that they are outside of this square. We said that it's outside when it is -3 or +3. So we test for outlier by calculating like the residual minus the average, that in this case is 0, divided by the square root of the standard mean of the error. So we calculate for these four numbers, and because any of these numbers it is -3 or +3 beyond of this range, we can say that this data it is not significant, that it's outside of our linear. I would like to show you how our counterplot will look like. The counterplot can be made by the evaluation of the model that we already obtained from the field height deviation. So in this case, because we are working with 3 factors, but Excel has not the ability to plot in a 3D dimension, we have to establish 2 cases. One, when C is minus, that corresponds to these 4 cases, and another case where C is plus, that corresponds to these other 4 cases. So we know that we are in the correct way if in our 4 points from corresponding that evaluation from 1, -1 in the horizontal axis and 1 to -1 in the vertical axis corresponds to these numbers that we already calculate, and because it is true, we know that this is correct. And now we do we color the ones that are close to 0, because this is what we want. We want 0 because this is not a problem of maximum or minimum. This is a problem when we want the exact filling height of the sodas. So in this first case, we have all of this range to work with, and if we evaluate this same thing but with the +1, we only can work in this little range. So it is better if we work with C minus. We have these pixels that can be softened if we do a bigger plot. This is a plot of 200 for 200, and we can see all of this range that we can work on.